Hola amigos, so now let's continue with takeoff performance, and that's an accelerated flight. And we know the aircraft is moving on the runway starting from 0 velocity towards accelerating towards the takeoff velocity till SG, till the start of this rotational distance, where when the aircraft moving on the runway achieves this stall velocity, and then it nose up and flare for 3 seconds and then move towards this transition phase where it pull up towards this climb phase of SC and covering SC distance. This distance is all measured on the ground. Okay, so now here you are seeing this ST distance which we have done earlier lecture in the earlier lecture, and here when the thrust is greater than drag and the frictional force, which is mu times W minus L, when the aircraft is moving on the ground or the runway, it will experience frictional force on its wheels, and those wheels will create friction. Okay, so that friction will be much lesser than this thrust. So on approximating this, that thrust is greater than drag and frictional force, SG will turn out to be 1.44 times W takeoff square divided by G times rho infinity times S landform area multiplied by CL max times thrust T. Okay, and if we now observe this more clearly, we will see that SG, the ground distance, is function of W by S. If we take W down with T by W, we will have W by S and T by W in the denominator. And if we say that W by S is higher, then SG will be higher. Or say when the planform area of the aircraft is less, then SG will be high. Okay, and if the thrust weight ratio, that is T by W, is high, then SG will be low, because more the acceleration and lesser the weight, then obviously it will take less time to take off from the runway, or say SG will be less. And if it has CL max of higher value, that is if CL max is increased by using flaps or other devices that increases the CL max of the wing or whole aircraft, then SG will decrease. Okay, it will move, it will take off from the runway in a lesser distance. And if the density is here you are seeing that density is rho, and here SG is inversely proportional to rho square, which is because of this thrust. Downwards thrust is also directly proportional to rho, and here thrust and thrust as a function of rho and rho in the denominator are taken into consideration, and which is why SG is inversely proportional to rho square. So more the density, lower the SG distance. Or say the colder the day or the lower the altitude at which the aircraft will be flying or taking off, the higher will be the lower will be the SG distance. Okay, so now moving on to this SR, that is the rotational distance. Okay, so the rotation distance is covered by moving this aircraft. The aircraft has achieved the takeoff velocity we take off at this SG distance, at the end of this SG distance, and now the aircraft is moving with this takeoff velocity for 3 seconds. Okay, these all are assumptions for preliminary design considerations, so do not worry about that. These are this SR distance is the time, and the time multiplied by the velocity with which it will be taking off. So distance is equal to speed into time. Speed at which it is taking off is v takeoff multiplied by the 3 seconds with which it is flaring from the runway. Okay, the moment at which the landing gear or the wheels of the aircraft leaves the runway. Okay, so the wheels of the aircraft when move with the aircraft above, then this distance SR is taken into consideration for 3 seconds while moving with velocity v takeoff. Okay, so moving on to the next phase of this whole takeoff performance, we have this pull-up maneuver. Okay, this pull-up maneuver will be discussed in more detail in next topic, but for the covering of this transition distance STR, we have done a little bit over here that this transition distance is this much. Okay, the aircraft has flared for 3 seconds and it is now pulling up. Okay, so the aircraft when pulls up, it is assumed to have a CL of CL max. Okay, so but with the consideration of regulatories of this aviation, we take CL to be 0.8 times of CL max while pulling up. So it is, if in the question it is given, then you can take 0.8 times of CL max, otherwise you take CL max only. Okay, so there is no confusion. So STR distance, this distance is measured by taking this pull-up maneuver into consideration. So the aircraft is pulling up in this phase of this pulling up phase. This is the phase, and this radius is the radius of this curvature which the aircraft is following. Okay, so this gamma, if we want to know, it will come from this climb angle. Okay, so this climb angle after the transition phase, it follows the climb path, it will have this climb angle gamma. So this gamma can be computed by sine gamma. Okay, so sine gamma is perpendicular upon hypotenuse. Perpendicular can be approximated because this curvature is quite high, because when pulling up it has a very huge curvature. So this curvature STR will have this radius R and angle gamma. So this sine gamma will give us perpendicular STR upon hypotenuse R, which is given over here. And STR, this distance can be approximated as this horizontal distance. So this STR is an approximation as R times sine gamma, and this R will be computed in our next lecture when we study pull-up maneuver. And moving on to this climb phase, we have the aircraft moving from this pull-up maneuver to the climb phase, covering a distance SC on the ground we know while climbing, specifically we are talking about steady climb over here. It is an unaccelerated climb. Okay, we started with accelerated flight. We have seen the acceleration from this to SD, and in this rotational phase and the transition. But here in the climb phase, we are considering this steady climb. Okay, so these can be assumed because for the preliminary design conditions. Okay, so don't need to worry about that. And steady climb is given by the rate of climb is given by this v times sine gamma. If you remember, we have done this earlier. Rate of climb is v takeoff times sine gamma. Because if the aircraft is following the flight path, or this climb phase is followed by the aircraft, then thrust is the forward force towards the flight path, drag opposite, lift perpendicular to flight path, and weight always towards the center of the earth. Okay, so, or downwards you can say. So on resolving these forces along the flight path, we have T minus D divided by W as sine gamma. Okay, so this sine gamma is T minus D by W, and this sine gamma when multiplied by velocity, it gives us the vertical velocity component with which the aircraft is climbing. Okay, or say the amount of vertical distance covered in a given time is the rate of climb, and that is exactly vertical component of velocity, which is v takeoff times sine gamma. And sine gamma we have deduced that it is sine gamma is T minus D by W. And now if we see this, if we want to compute this STR, or say let's say STR is computed. Okay, from this STR, okay, from this pull-up maneuver, STR is computed. Okay, so moving on to the climb SC, we have tan gamma, this tan gamma perpendicular on base. Okay, perpendicular is this much distance. 15 is from screening height till this 15 meter from the horizontal surface or the runway. It is the total height from the runway to the screening height. For propeller plane, it is 15 meter, and if in the question it is given it is a jet aircraft, then it will be replaced by 11 meter. So here we have done for propeller plane. That's why we have 15 over here. And STR is deduced from this, and tan gamma perpendicular 15 minus STR, because 15 is the total distance from runway to the screening height. Okay, so 15 minus STR divided by base is given by this tan gamma, and from here we can compute the climb distance on the runway, or say on the ground. SC is then 15 minus STR divided by tan gamma. So now this last topic of this lecture is the forces and their variation with velocity. Okay, actually it is variation with v square, velocity square, and their variation with ground. When the aircraft is moving on the runway, then how does they vary the thrust, drag, lift? How do they vary with the distance or with the velocity? With v square actually. Okay, so here we can see that thrust is directly proportional to v square. Okay, we know, but thrust required, we know that it is parabolic graph. T is this, thrust required is this graph, we know. It is not plotted over here, it is given by the curvature like this, parabolic curve. So here it is plotted against v square. When thrust required is plotted against velocity v, then it is given by the parabolic curvature, but here it is v square, so it will be a linear curve. Thrust for a jet aircraft here is given by a linear curve. Okay, here the computation was with respect to the propeller aircraft. This is just for the reference, so here we can use any jet or propeller. Here we have done the jet aircraft performance. So the thrust force along the distance keep on decreasing very slightly, okay, because the slant height, as you can see, is quite less. Similarly, if we observe this lift force and drag force and this frictional force, actually if we observe now, frictional force will keep on decreasing, because as the aircraft is moving on the runway, okay, so it is moving on the runway, it has to fly, let's say it has to move up from the runway, so the lift or the upward force will keep on increasing with the distance. So the frictional force between the runway and the wheels of the aircraft will keep on decreasing. So that's why we have this downward slope, or say the friction force is decreasing along the distance. So as the aircraft is accelerating, the drag on the aircraft will keep on increasing, and the drag is also like the parabola, but here we know it is with respect to v square, and lift is also with respect to v square, therefore they have linear variations. So their linear variation will like for drag is this, is drag will be increasing like this, and lift will obviously increase with the velocity. They are linear. But now if we observe the total force, here we have observed them individually, okay, so the total force is the mass into acceleration, or say the total force with which the aircraft was moving along the ground. Okay, so what was that force? It was T minus D minus mu times W minus L. Okay, so this total force is actually the difference between this thrust minus this line is actually D minus D plus W mu times W minus L. Okay, so this line is D plus mu times W minus L. So thrust minus this force, that is D plus W minus L, will be T minus mu times W minus L. So this net force, this between this thrust and this line, is what is driving the aircraft in the forward motion along the ground. So thank you for this lecture. We'll continue in next lecture.